Welcome to the batteries training. This training will address the question of how to store energy from the solar resource by focusing on technology that are used to store electricity from solar energy production. This training has been realized in the context of the European Solarize project that focuses on the adoption of solar energy in the Two Seas region. It is part of the training package emerging from the Solarize project that is pointing out some of the key topics on solar energy. We will start this training by presenting some generalities about the storage of energy. Then we will focus on the electrochemical form of energy storage that correspond to the batteries technology. And then we will have a look about why it is important to store energy, especially in solar application, before describing several types of battery technologies that are used in solar applications. And we will finish the training by making some comparison between these different batteries technologies and also with other forms of energy storage. So let's start with some generalities about energy storage. First of all, it is important to have in mind that energy can be stored under 5 main forms, but that are radically different. Indeed, each form allows to store different natures of energy in different quantities and is also able to restore it in very different time. Then the selection of the energy storage form and its associated technology is clearly dependent on the application. Thus, we are presenting here on the left the 5 main forms under which energy can be stored, with some of their associated technology. And on the right, a graph that compares them in terms of their capacity to store energy versus their discharging time. So firstly, the mechanical form concerns mainly the pumped storage hydropower technology that is used to store large quantity of energy, as the compressed air energy storage technology to a lesser extent, and also the flywheel technology that can be stored far less amounts of energy but which benefit from a very fast discharging time that have a particular interest for transport application. The electrical form concerns mainly the capacitors that are used to store very small amounts of electricity for electronic devices mostly, and it concerns also the new superconducting magnetics energy storage technology that is also used for short duration storage but which is still under development. The thermal form of energy storage is regularly used for application that needs to store heat for around an hour to a few months, such as the domestic hot water that is stored in a tank, for example, or for some solar application like concentrated solar power plants. The chemical forms concern several technologies like hydrogen or biofuels, but is more used to store a large amount of energy for a long period of time. And finally, the electrochemical form that concerns mainly the batteries that we discuss in this training. But before going a bit further into the different battery technologies, it is important to remind ourselves that in practice, almost all of the grid-connected operational store capacity in the world is under the mechanical form through the pumped storage hydropower technology with around 170 gigawatts. The rest of the operational store capacity is distributed between the thermal form, some of other chemical forms, and the electrochemical form that represent around 2 gigawatts. Then these 2 gigawatts of grid-connected electrochemical energy storage are distributed into different battery technologies that have been developed within the last few decades. And as you can see in the diagram on the left, the most dominating technology for all types of application is the lithium-ion battery with almost 80% of the global capacity. And in 2020, this trend seems to increase according to a recent Chinese market analysis, where lithium-ion batteries represent almost 90% of the market, moving from 1.6 to around 9 gigawatts, which correspond to an increase in their capacity by a factor of 6. Moreover, the global capacity has also been multiplied by around 6, going from 2 gigawatts to more than 10 gigawatts, which shows us the great dynamics of the battery market in the world. Thus, as part of this training, we will detail the battery technologies that are used to store electricity from solar energy production. But before giving more details about battery technologies that are used for solar applications, it is important to remember the principle of electrochemical storage, which is the basis of the operation of a battery. From a general point of view, the electrochemical energy storage is mainly based on a chemical reaction that exchanges electrons, or in other words, electricity. Then the principle of a battery is to implement such a chemical reaction of oxidation or reduction, allowing the use of these exchange electrons or electricity for another application. To do so, a battery requires two electrodes, an electrolyte, and an electrical circuit to make electrons or electricity circulate. This electrical circuit links the two electrodes that are always polarized as positive and negative, and that sandwiches an electrolyte that can be a liquid, a paste, or a gel, causing the reaction. Then, to never get confused about the functioning of a battery, there are 4 rules to remember. Rule number 1, the current always goes from the positive electrode to the negative one. Rule number 2, by convention, the electron flow is always opposite to the current flow. Rule number 3, the oxidation always occurs at the anode, and therefore the reduction always occurs at the cathode. To remember it easily, there is a mnemonic with the concordance of the first letter. Anode and oxidation start with a voyelle, and cathode and reduction with a consonant. Rule number 4, remember the word Olrich. It will remind you that the oxidation is losing an electron and the reduction is gaining an electron. During the discharge, if I'm applying these 4 rules, the current always goes from the positive electrode to the negative one, then the electron flow is going opposite. And since the oxidation always occurs at the anode and that oxidation is losing an electron, then the negative electrode is the anode, and so the positive one is the cathode where the reduction occurs. In the electrolyte, only the positive and negative components are moving, so-called cation and anion respectively. And during the discharge, the positive components, called cation, are moving toward the cathode in order to get reduced by gaining electrons. The negative components, called anion, are then moving to the anode in order to get oxidized by losing electrons. Then during the charge, everything is inverted, but the 4 rules are still valid. Indeed, since the battery can be seen now as a load that is being recharged, the current is still going from the positive to the negative electrodes of the current generator, which is now here in the middle. Then from the battery point of view, the current is going from the negative to the positive electrode, and then the electrons are going opposite. Thus, the place where oxidation and reduction occurs are also inverted. And then the most important thing to remind is that the name of electrodes are also changed. Thus, the place where oxidation and reduction occur are also inverted. And then the most important thing to remind is that the name of electrodes are also switching. Indeed, in order to respect the rule number 3, the oxidation occurs at the anode and the reduction always occurs at the cathode. Therefore, since these chemical reactions are changing place from an electrode to the other one, then the name of these electrodes are also changing. And of course, anion and cation are also going opposite in the electrolyte. So to summarize, the electrochemical battery is a device that implements oxidation-reduction reaction on each of its electrodes in order to exchange electrons that are going way and back through the electrical circuit thousands of times during its lifetime. As the anion and cation are also going way and back, but through the electrolyte. Now that we have seen how a battery works, we can ask ourselves why it is important to store energy, especially in solar application. Well, if we take a basic example of a typical house with solar panels, and we look at the consumption curve of this house and the production curves of its solar panels, we can clearly see that it's not fitting. In other words, the energy is produced in the middle of the day when the consumption is quite low and doesn't require that much of energy, but is not available at night or in the morning when people need it the most. Thus, the excess of electricity produced is exported to the grid. Then, in order to avoid exporting the energy and maximize self-consumption of the solar energy, a storage system is required to store a part of the solar production during the day to be used later when we need it, especially during the consumption peak in the evening and in the morning. Therefore, the principal aim of a battery storage for solar application is to manage the source demand shift. But offsetting the mismatch between the production and the consumption is actually a reality at 2 different levels. A reality on the consumption side, where each consumer has its own curve of needs, and on the production side, where the producer needs to deal with the intermittence of the solar resource that can be predictable, like day and night cycles or season, or unpredictable, like clouds. There are several other functions and interests of using a battery storage system, but it's not discussed in this training since it's very depending on the system and its application. So let's move now on the main purpose of this training. We'll give from here some details on the batteries technologies that are used to store electricity in solar applications. It concerns mainly 4 technologies: lead-acid batteries, 2 nickel-based batteries, lithium-ion batteries, and flow batteries, for which we will focus on one example. For all these technologies, detail will be given on 4 main aspects: the chemical aspect, where chemical component and equation of the reaction for each technology will be specified; technical aspects that will concern all the key figures of the battery performances, its operating temperature, its lifetime, and an order of magnitude of its cost; the environmental aspect, in order to realize the impact of these technologies on the environment and to better perceive the challenges they will have to face; and the list of the applications for which each technology can be used. All this detail will be written on the slide in order to share with you these informations, but each of them will not be necessarily discussed. So don't hesitate to stop the video to catch information that are relevant to you. The lead-acid battery is the first type of rechargeable battery ever created in 1859 by the French physicist Gaston Planté. They are composed of a lead electrode and another one in lead oxide and an electrolyte of aqueous sulfuric acid. Compared to newer types of rechargeable batteries, lead-acid batteries have one of the lowest energy density. Despite this, their ability to deliver high current means that the cells have a relatively high power-to-weight ratio. These characteristics, along with their low cost, make them attractive to use in motor vehicles to provide the high current required by the starter motors. Because they are inexpensive compared to newer technology, lead-acid batteries are still today widely used even when other designs could provide higher energy densities. Large format lead-acid designs are widely used for storage in backup power supplies in cell towers, high availability environments such as hospital and standalone power systems. For these roles, modified versions of the standard cells can be used to improve storage time and reduce maintenance requirements. Nevertheless, the weak point of this technology is the formation and dissolution of lead sulfate on the pure lead negative electrode over the charge and discharge cycles, which is clearly decreasing its performance with age and limiting its lifetime. New lead-acid systems have carbon added to this electrode to overcome this problem. Anyway, the biggest issue with lead-acid batteries occurs at the environmental level. Lead is highly toxic and recycling it can lead to pollution and contamination of people, resulting in many lasting health problems. However, lead recycling is one of the easiest to achieve, where up to 100% of lead-acid batteries can be recycled and reused for a second life, which in this sense limits its relative impacts to the environment. As an example, 99% of lead-acid batteries in US have been recycled between 2014 and 2018. But this ratio is in reality fluctuating from 60% to 95% since 1982. The nickel-based batteries used for solar application mainly concerns the nickel-iron batteries and the nickel-cadmium battery. The nickel-iron battery is composed of a positive nickel oxide hydroxide plate and a negative iron plate with the potassium hydroxide electrolyte. It is a very robust battery that tolerates abuse, overcharge, over-discharge, and short circuit, and can have a very long life even when treated as such. It is often used in backup situations where it can be charged continuously and can last for over 20 years. The ability of this battery to survive frequent cycling is due to the low solubility of the reactant in the electrolyte. The formation of metallic iron during charging is slow due to the low solubility of ferrous hydroxide. While the slow formation of iron crystal preserves the electrodes, it also limits high rate performance. These cells charge slowly and can only discharge slowly. Nickel-iron cells should not be charged from a constant voltage supply because they can be damaged by thermal runaway. The internal cell voltage drops at the start of gassing, which increase the temperature, which increase the current draw and thus further increase gassing and temperature. The nickel-cadmium battery is composed also of a positive nickel oxide hydroxide plate, but with a negative metallic cadmium plate and the same potassium hydroxide electrolyte. Compared to other types of rechargeable battery, they offer good life and performance at low temperature with average capacity, but the significant advantage is the ability to provide nearly full rated capacity at high discharge rates. They can discharge in 1 hour or less. However, the materials are more expensive than those of the lead-acid battery and the cells have high self-discharge rates. In addition, nickel metal hydride and lithium-ion batteries have recently become commercially available and less expensive, with the former type now rivaling nickel-cadmium batteries in cost. Where energy density is important, nickel-cadmium batteries are now at a disadvantage compared to nickel metal hydride or lithium-ion batteries. About the application, many rail vehicles use nickel-iron batteries, but due to its low specific energy, low charge retention, and high manufacturing cost, other types of rechargeable batteries have replaced the nickel-iron batteries in most applications. Nevertheless, the technology has regained popularity for off-grid applications where daily charging makes it an appropriate technology. Nickel-iron batteries are being studied for use as combined batteries and electrolysis for hydrogen production for fuel cell cars and storage. This new functionality could be charged and discharged like conventional batteries and would produce hydrogen when fully charged. The advantage of nickel-iron batteries is that they do not have the lead or cadmium of lead-acid and nickel-cadmium batteries, which must be treated as hazardous materials. But the challenge concerns more about the nickel supply and all its related issues. For the nickel-cadmium batteries, they were once widely used in portable power tools, photographic equipment, flashlights, emergency lighting, radio control, and portable electronic devices. The superior capacity of nickel metal hydride batteries and their recent lower cost have largely supplanted the use of nickel-cadmium. In addition, the environmental impact of eliminating toxic metallic cadmium has contributed significantly to the reduction in their use. In the European Union, nickel-cadmium batteries can now only be supplied for replacement purpose or for certain types of new equipment such as medical devices. Larger vented wet cell nickel-cadmium batteries are used in emergency lighting, backup power, uninterruptible power supplies, and other applications. About the lithium-ion battery, they are generally composed of a negative electrode made of carbon, a positive electrode made of metal oxide, and an electrolyte as a lithium salt in an organic solvent. And as you can see on the diagram, there are plenty of possible metal oxide here in orange and electrolyte here in light blue, which allows lots of possible combinations for lithium-ion batteries. The most common negative electrode used commercially is graphite. And for the positive electrode, it is generally one of the listed materials here in orange, like a layered oxide, such as lithium cobalt oxide, a polyanion, such as lithium iron phosphate, or a spinel, such as lithium manganese oxide. And recently, graphene-containing electrodes based on 2D and 3D graphene structures has also been used as electrode components for lithium-ion batteries. The electrolyte is typically a mixture of organic carbonates containing lithium-ion complexes. These non-aqueous electrolytes typically use anion salts as listed here in light blue. Depending on material choices, the voltage, energy density, lifespan, and safety of a lithium-ion battery can change dramatically. The current effort has explored the use of new architecture using nanotechnology to improve performance. Areas of interest include nanoscale electrode materials and alternative electrode structures. Pure lithium is highly reactive. It reacts vigorously with water to form lithium hydroxide and hydrogen gas. Thus, a non-aqueous electrolyte is generally used and the sealed container rigidly excludes moisture from the battery pack. Lithium-ion batteries are more expensive than the previous battery technologies that we have just seen, but they operate over a wider temperature range with higher energy densities. Thus, they are providing lightweight, energy-dense power sources for a large variety of devices, as you can see on the list of their applications, and are especially becoming the most promising technology for hybrid and electric vehicles. In addition of their common use for cell phones now, that is why this technology is currently completely flooding the market. Nevertheless, the lithium-ion batteries do have an environmental impact, and the biggest risk to the environment comes from its production. Finding the source material for the electrolyte solvent has a big overall effect in the production phase. In production, lithium is usually found in compound form due to its reactive nature, and processing this material is detrimental to the environment. Another factor is the sourcing of this material. As lithium is most abundant in salt flats, most of it is mined there. Mining in the salt flats requires large amounts of water, which leads to water eutrophication, transport emission, and lack of water for local population and wildlife. When leaching, toxic chemicals are also used. This requires waste treatments, and there is a concern of them not being disposed of correctly. When lithium-ion batteries have reached their useful life, they are limited in how they can be disposed of, and most batteries end up in the landfill. The flow batteries are a type of rechargeable battery where the two chemical components of its chemical reaction are in liquid state and are pumped through the system on separate sides of a membrane. Ion exchange occurs across the membrane while the two liquids flow in their own respective spaces. Although they have technical advantage over conventional rechargeable batteries, such as potentially separable liquid tank and virtually unlimited longevity, current implementations are comparatively less powerful and require more sophisticated electronics. In general, it is important to remember that its energy capacity is a function of electrolyte volume and its power is a function of electrode area. Among this type of battery, we present here the zinc-bromine flow battery, where a zinc bromide solution is stored in two tanks. When the battery is charged or discharged, the solution or electrolytes are pumped through a reactor stack and back into the tanks. One tank is used to store the electrolyte for the positive electrode reactions and the other for the negative one. During charging, metallic zinc is plated from the electrolyte solution onto the negative electrode surfaces in the cell batteries. The bromide is converted to bromine at the positive electrode surface and is stored in a safe, chemically complex organic phase in the electrolyte reservoir. During discharge, the reverse process occurs. The zinc metal plated on the negative electrodes dissolves in the electrolyte and is available to be plated again in the next charge cycle. It can be left fully discharged indefinitely without damage. The main characteristics of a zinc-bromine batteries are the following. High specific energy compared to lead-acid batteries, 100% depth of discharge capacity on a daily basis, no shelf life limitation, as zinc bromide batteries are not perishable, unlike lead-acid and lithium-ion batteries, for example, scalable capabilities. The disadvantages include the need to be fully discharged every few days to avoid zinc dendrite that can puncture the separator, the need every 1 or 4 cycles to short the terminals on a low impedance shunt while running the electrolyte pump in order to completely remove zinc from the battery plates. And finally, low power density during charging and discharging, resulting in high energy cost. This type of battery have a particular interest for remote telecom sites applications, where significant fuel saving are possible when they are operating under low electrical loads and high installed generation conditions by using multiple systems in parallel to maximize the benefits and minimize the drawbacks of the technology. Nevertheless, they still compete to provide energy storage solutions at a lower overall cost than other energy storage systems such as lead-acid, lithium-ion, and others. From an environmental point of view, the biggest problem of this battery is the use of bromine, which is toxic and has to be treated as a hazardous material. And the filtration process of bromine involves a high negative impact to the environment. We are about to start now the last part of this training, where we are going to compare different battery technologies and also some of the types of storage systems for different parameters. We start here with the comparison of the specific energy versus the specific density of several types of electrochemical rechargeable batteries that is globally summarized their performances. Higher is the specific energy and lighter is the battery technology, higher is the specific density and smaller is the battery technology. And as you can see in terms of pure performances, lithium-ion technology are clearly dominating. Nevertheless, some technology are also of interest, especially the lithium-ion polymer batteries, the sodium sulfate batteries, and the sodium-ion batteries. We are comparing now the rated power versus the energy stored for some batteries technologies as for other types of storage systems by specifying their discharging time range. We can see here, for example, that the flywheel technology or supercapacitors are clearly made for application with a quite short discharging time and do not require large amounts of energy stored, whereas chemical forms of storage like power to gas or hydrogen are made for long-term energy storage with a very high rated power and energy store capacity. In between, rechargeable batteries can fit with application requiring a discharging time from around some minutes to some days, where thermal storage can go up to some months. But since the energetic density of batteries is way much higher than that of thermal storage, this makes them a much more practical technology for small or mobile applications where volume and weight are critical parameters. In terms of investment cost, it is an essential parameter because it determines the overall cost of energy production and thus a great part of the final cost to the consumer. Therefore, this graph compares the investment cost per energy unit and the cost per power unit for 4 batteries technologies, 3 different mechanical storage technologies, and supercapacitors. But it is important to remind ourselves that the values here are given just as an order of magnitude that allows us to compare different types of technologies. The effective investment cost of each technology is very hard to determine accurately because it's depending on a huge number of parameters and only correspond to a specific application from a specific company to a specific place at a specific time. Anyway, we can still clearly see that compressed air energy storage and especially pumped hydropower technology have the lowest investment cost per unit of power and energy. That is why 96% of the total grid-connected operational store capacity worldwide is made with this technology. For the flywheel and supercapacitors, they have even a lower cost per power unit since they are made to deliver energy at high power rates. But in terms of energy, since they are not made to store large amounts of energy, their investment cost per energy unit is the highest. About the batteries now, lead-acid technology appears with the lowest investment cost, which explains why this technology has been chosen until now, especially for transport applications. But for solar application, it remains an interesting technology compared with nickel-cadmium, lithium-ion, and red flow batteries that have a higher capital cost. But this parameter has to be coupled with the expected lifespan of the battery technology and see which one is the most interesting in terms of investment plus maintenance cost over the whole project lifetime. Here we are looking at the efficiency versus the lifetime of different storage technologies. The ideal storage system would have the highest efficiency with the longest lifetime or number of cycles. On the graph, only supercapacitors and flywheels have these two properties, but once again they are limited in terms of store energy capacity. Nevertheless, lithium-ion batteries have the best efficiency and lifespan compared to other battery technologies. It would be interesting then to compare different battery technologies for the storage part of a PV system over its whole lifetime, since lithium-ion batteries are certainly more expensive than lead-acid, for example, but have a higher expected numbers of cycles. Then that would help to choose the most suitable technology, at least from the financial point of view. To finish, this graph illustrates the maturity of different storage technology using the technology readiness level parameter. This graph is provided as an illustrative example in order to compare the different technologies since their research and development is progressing rapidly and their technology readiness level is always moving, and also because it is a subjective parameter. Anyway, we can still clearly see that pumped hydropower and lead-acid batteries are the most mature technologies, since they have been used for several decades now, closely followed by compressed air storage, nickel-cadmium batteries, and after that the lithium-ion batteries, which are growing very quickly over the last few years, and the flow batteries and flywheel, which have demonstrated their feasibility, but are still struggling to develop in a sustainable way worldwide. And finally, with regard to hydrogen, supercapacitors, and thermal storage, they have several operational industrial pilots and are on the way to develop their commercialization over the coming years. Thank you for your attention.